piece of work was done around 2014, 2015. And at the time I was with Nelson, which is the leading market research and analytics company. Okay, so Nelson is actually, just to give you a brief overview of what Nelson is doing. Nelson is basically a market research company. So the company has actually operations in 100 plus countries and regions worldwide. And at that time, the Singapore office was actually the headquarter, regional headquarter of the Asia Pac region. Okay. So this piece of work was actually offered as a final year project. It's a collaboration between the data science team within Nelson at the time, together with the School of Department of Statistics and Applied Probability. So this project was actually offered as an undergraduate final year project, and you can see that the student who enrolled on this project is actually on the left-hand side of the screen. And myself is actually in the middle, and that time, Timothy Bang was actually my manager. Actually, when Prof. Chang invited us to come here to give a talk, the team actually wanted to actually come and speak because he was still with Nelson, but unfortunately, because of timing, he actually received a posting and has actually gone out to take up a new posting over at Chicago. So here, I'm doing no comment.
Oh, sorry.
Okay. So here today I'm filling in for him since I also know quite well what has been done in this project. Okay, so this will be the overview of my talk today. Basically, I'll give you a brief summary of what the project is about, leading to the accumulation of the use of the particle swarm optimization technique to actually give us the final piece of the puzzle that we are trying to build, the solutioning process. Essentially, we use particle swarm optimization to solve the problem that we are facing in this project. And instead of using the conventional particle swarm optimization technique, we are going to use a modified form, because the problem that we have in this project is actually a discrete optimization problem, instead of the conventional continuous optimization problem that you may be familiar with. So I'll be presenting the high-level overview and ideas behind the modified particle swarm optimization technique that we have proposed. If you are interested, later I also have a sort of link to the paper that we have published in one of the conferences on natural computation. So you may want to actually go and pick up the paper to know more about the technical details. And also, I'll end by looking at some of the results and discussions and also a conclusion of future work. Okay, so what is it that we are trying to do? Now, as you know, Singapore is actually a rapidly aging society, right? As of 2010, as I put here, our total fertility rate was only 1.16, which is way below the 2.1 birth that we need to actually replace ourselves. Okay, so if you project this trend forward, by 2030, around 2030, about 30% of the local population will be aged 65 years old and above. Okay, so we are actually facing a big time bomb here because the population is aging rapidly, and with this, we don't have enough economically active adults to actually continue working to support the aging population. So this got our leaders, political leaders, and government very worried. So that's why the CPF board, which is actually the government agency in charge of all our retirement savings, because every month when you work, a portion of your salary actually goes into these CPF accounts for your retirement savings. So the CPF board then commissioned a study, okay, to actually look at the retirement adequacy and what are the issues related to retirement and also healthcare needs for the local population aged between 45 to 85 years old. Okay, so a large-scale survey was proposed, and this survey actually has a total of about 32,000 respondents, and an open call was actually called by the CPF board
among the different market research and data collection agencies to actually provide the services for, to collect data for this survey. So Nelson, being one of the biggest local agency in Singapore, won the contract to actually perform 2 waves of this survey. Okay? The inputs from the survey will be used to actually formulate policies in terms of aging, active aging, and also whatever healthcare needs and also infrastructure that may be required as our citizens age. Okay? So that will form part of the policy formulation. Okay, so this survey is basically a longitudinal study over 10 years to be conducted over 5 waves. So Nelson, as I mentioned, won the contract to perform wave 1 and wave 2 of the data collection process. So you can see in terms of timeline, on the odd years, on the even years, we'll be performing the data collection process, and then in the odd years, the CPF board will be doing some analysis on the data collected in the previous wave. Okay. So for this longitudinal study, the original population or respondent size is actually 32,000 respondents spread out across different geographical locations in Singapore. So for Nelson's work, we have to actually collect data from these 32,000 respondents over a 12-month period, which is essentially from July 2014 to May 2015. And because of the size of the respondents, okay, this survey is to be conducted face-to-face. And each respondent will be interviewed by an interviewer over a period of about 2 hours. So there will be a list of questions and a questionnaire which the interviewers will then ask verbally the questions and the respondents will then provide their response to. Okay? Because of the size of the respondents, so we actually proposed to the board that we conduct the survey over 4 phases. Okay? And one of the requirements that the CPF board has for us is that across these 4 phases, okay, we have to actually reduce any potential for data collection bias. Okay? For example, we are not actually supposed to, in phase 1, just collect data from residents or respondents staying in the northern part of Singapore. And then in phase 2, western, phase 3, eastern, then the last phase, the southern part of Singapore. They wanted us to have a sort of a geographical spread that is consistent across the different phases. So that was one of the requirements. The other requirement is, of course, the manpower management issue. Because it's a large survey involving 32,000 respondents, so the company actually hired about 100 interviewers. And straight away, you can see that it becomes an assignment problem, resource allocation problem. How do we assign these 32,000 respondents to these 100 interviewers based on certain constraints? The obvious constraints will be each interviewer should have more or less equal number of respondents, so equal workload. The second constraint will be we do not want our interviewers to travel all over the island to cover their assignment. So we don't want an interviewer staying in the west to be given respondents staying in the east, so that they have to keep commuting from one end of the island to the other end just to complete their assignment. Okay, so these are some of the considerations when we are doing the fieldwork design for this survey. Okay, and in addition, I have also shown here. I've also shown here actually a sample listing of the kind of information that we get from the board. Basically, we have the name of our respondents, the age, the gender, the race, their residential address in terms of string text, and also the postal code. That is all the information we are given. We are not given the like the contact number and so on and so forth. So we have to actually find ways and means to actually arrange the interview timing with them. Okay, and also because sorry. It's actually not big if you consider that the residents population in Singapore is about 3-something million, of which close to, at present, close to about 20 to 30% are actually around retirement age. So this 32,000 listing was actually not generated by us, but was sort of shortlisted by the board. So we only took the listing from them, and we were told to actually contact these people and then get their response for the survey. Face-to-face is because a lot of these respondents, they may not be literate because they are actually between the age of 45 to 85 years old. especially the older people, they may not be literate. If you call through the phone, they may not be able to give you proper answer. So the best way to conduct this survey is actually face-to-face. So, okay, so the challenges will be to manage the manpower resources and to allocate the respondents to the interviewers subjected to certain constraints. And also because of we are only given the listings, so we don't know where the locations of these respondents are. Okay, in order to actually start our planning process, we have to manually convert, or not say manually, but computationally, algorithmically, we have to convert the text address of these respondents to their geographical locations. So we do geocoding of the addresses to get the lat-long position of our respondents, and then we plot it on the Singapore map so that we have an idea where our respondents are, together with overlay it with the locations of our interviewers where they are staying. This gives us the background to the problem they are trying to do, assignment of respondents to the interviewers. Okay, so you can see the black dots are the locations of a postal code. Okay, one postal code may have several respondents if they are staying in, let's say, HDB blocks, where one block you can have probably up to 20, 30 respondents, okay, depending on the selection by the board. Okay, and in order to maintain one of the requirements put to us by the board, which is to actually have consistent geographical distribution of the respondents across the 4 phases of the survey to be conducted, we then look at the sub-region respondents. So we look at the entire map of Singapore, and we can see that here, the Singapore map has been sort of carved out into different postal regions. So we are going to perform sort of clustering on the respondents in each of the postal region into 4 different subsets, so that geographically, across the different phases, we'll have a more or less even distribution. So that is what we have done prior to the execution of the fieldwork. Okay? So you can see that, for example, in Woodlands, Sembawang, which starts with the postal code 73. Okay, and Marsiling and Admiralty start with postal code 75. Okay, we have actually performed clustering of the respondents based on their geographical locations into the different phases. Okay, you can see that the phases are actually color-coded, and this will ensure that by doing this will ensure that the geographical distribution of our respondents will remain more or less consistent across phase 1 to phase 2 to phase 3 and phase 4. Okay. So as mentioned earlier, this project was actually offered as a final year project to the student to work on. So I have to actually state beforehand that this project, as compared to other presentations that you may see in this workshop or over the next day or so, may not be so heavy on theoretical research, because the focus is on applied research. Okay? And also because it's a final year project, so we have to actually strike a balance between doing something very theoretically fanciful and very pushing the frontier of knowledge to something that the student can actually complete within the 1-year time frame. So what we have asked the student to do is to implement, first of all, implement the basic PSO algorithm. Okay? So this basic PSO algorithm is nothing but the standard PSO algorithm used to actually optimize conventional continuous optimization problem. And we actually asked the student to test this PSO algorithm using some test function, some standard test function. Okay? So before I go into that, let me just briefly cover the historical background to particle swarm optimization. Basically, particle swarm optimization was proposed by James Kennedy and Russell Eberhard in 1995. And the motivation is, of course, from the natural observation of a swarm of birds and school of fish, where they actually have some swarm intelligence mechanism to locate the solution. Okay? And in particle swarm optimization, you have actually a swarm of particles, and each particles represent a potential solution in the domain search space. Okay, so this is the flowchart of the standard PSO process. Okay, basically, you start with deciding how many particles you want in the swarm, and then you randomly initialize particles in the domain search space. And then you evaluate the fitness of the particles, and then you look for the best solution for each individual particle as well as the population best. You update if it fulfills certain improvement criteria. If not, then you're going to update the velocity vector of the particle and hence its new position. And this process iterates until it meets some stopping criteria, such as the maximum number of iterations or the fitness function actually approaches or converges to some value. Okay? So that is essentially the idea behind particle swarm optimization. Now, this is basically the standard equation for a continuous particle swarm optimization problem, the standard particle swarm optimization problem. You can see here that the velocity vector is basically consisting of three components, or is influenced by three components. Its existing direction, the solution as seen by the particle, the best solution as seen by the particle up to the current point in time, and also the global best solution. And then to update the position of the particle is basically addition of the vector, velocity vector to the current position of the particle. So I have actually tried to geographically show here that basically the final position, the new updated position of the particle is actually a composition of the term A, term B, and term C, as highlighted by the equation here. Okay, so we asked the student to implement the basic particle swarm optimization technique, and in order for him to have a feel that his implementation is correct, we asked him to actually test this particle swarm optimization technique on 4 commonly used functions. I think all of you, or most of you may have heard of the Maconic function, the Essen function, the shuffle function too, and also the holder table function. Basically, these are quite pretty standard toy problems to actually test the performances and the correctness of a PSO algorithm. Okay. So for the first function, it's basically the optimal solution is actually located around here, the black region, okay, where x is around -1 and y is -2, as can see from the global best position as identified by the PSO algorithm. So the student basically play with the PSO algorithm that he has implemented, and by setting different initial parameter and social and cognitive parameters, he just want to show that with increasing swarm size, the convergence rate of the algorithm actually gets better, okay? Which is quite intuitive, because if you increase the swarm size, you are actually increasing the potential number of solutions that you are evaluating in one iteration. So this will actually help to speed up the search process. Okay, and then the next problem is basically to locate the optimal solution here as indicated by x2 equal to 0 and x1 equal to 0. So again, he actually set the initial parameter and the swarm size and also the velocity range, and look at how the social and cognitive factors actually influence the speed of the search process. Okay, so by having bigger search size, actually the search process becomes more chaotic, and at a point where the search size is too big, the algorithm actually fails to converge. So in a sense, he get an idea that maybe to have a good performance, the social and cognitive factors should not be too big, probably around 1 to 1.5. And also for this shuffle function too, what he's trying to look for is actually how the number of iterations actually varies with the fitness function. So he's trying to show that his algorithm is able to converge with increasing number of iterations in order to locate the solution to this function. And the last one is basically using PSO, the standard PSO algorithm, to look for the solution at different corners of this table holder function, okay, and changing the speed of the velocity vector. Okay, so this series of simple exercises is just to evaluate that his implementation is correct before we go on to actually modify the algorithm to suit our problem needs. Okay, so how do we actually modify the algorithm? As mentioned, what we have done is basically to geocode the location of our respondents, okay, and then to perform clustering such that we have almost a similar geographical distribution of our respondents across the different phases. So you can see that basically this is a discrete combinatory optimization problem where we have m clusters of respondents and we have n number of interviewers, and we need to assign these n clusters of respondents to these n interviewers so that one cluster is assigned to at most one interviewer, and one interviewer can have more than one clusters of respondents. So it's basically a discrete problem as compared to the conventional continuous optimization problem. Okay. So we propose to actually modify the standard PSO algorithm in 3 different ways. Okay. One, we want to preserve the fact that the position of our particle is still dependent on the existing position of the particle and also the particle best solution as well as the global best solution. Okay. So in order to do that, we make sure that the solution of our particle, the solution element of the particle can come from either the existing position, the P best, or the G best position. Okay. And in order to make sure that we strike a balance between the influence of these 3 different positions, we make use of our velocity factor and define it such that it becomes some probabilistic control, such that the new position of a particle then can have a selection from this, or this. Okay. So how do we do that? Okay, this is basically the algorithm that we have proposed. Essentially, it's the same flow chart that we've seen previously. It's just that the modification affect the blue parts that I have highlighted here. The first modification that we did was, instead of a continuous vector of values, because to deal with the discrete optimization problem, we have to have discrete representation of the particle position. So here we actually look at changing the vector to a metric, n by n metric, where the rows will show you the number of clusters of respondents we have, and the column the number of interviewers. So for this simple example of 4 clusters to 3 respondents, you can see that for the cluster 1, it has been assigned to interviewer 2. Okay? And for cluster 2, it has been assigned to interviewer 1. Cluster 3, it has been assigned to interviewer 3, and cluster 4, it has been assigned to interviewer 1. So that is how we actually use this binary metric representation to actually express the solution of our particles for the discrete problem. And then, to keep to the principle that the position of the new particle is affected by both the existing position and the P-best and the G-best solution, we introduce the update equation for our discrete version of the particle swarm algorithm as such. Here I gave a simple example. We make use of Q1 and Q2. Q1 in this case actually serves the function of the cognitive factor in the conventional particle swarm optimization technique for the continuous optimization problem. Q2 is the social factor, and Q3 is basically telling the solution to actually select from the V metric or select from the current position of the particle. So if you refer to the simple example here, this is the difference between the P-best and the X metric. This is the difference between the G-best and the X metric. By randomly assigning a value between 0 and 1 for Q1 and Q2, we can then start to select comparison. If Q1 is greater than Q2, then I take the row from this metric. If Q2 is greater than Q1, then I'll take the row from the second metric to define my new velocity metric. Once I have the velocity metric, then I will have another Q3 factor, which is actually a random number, which is either 0 or 1. If it's 1, I'll update the position of the new particle by taking the row from the velocity metric. If no, then I'll just basically take the original row from the existing position. This will give me the new particle position, which is the new solution in the current iteration. Okay? So basically, nothing fanciful. We are just trying to preserve the principle and the optimization technique of the conventional particle swarm optimization technique in this discrete version. Okay. Next, we apply this modified version to our problem. Okay. Essentially, if you still recall, our problem is actually to ensure that our interviewers have equitable amount of workload, okay, so that we don't see the situation where one interviewer has maybe thousands of respondents to handle, and the other interviewer maybe only have 4 or 5 respondents, which is not good. And also, we want to minimize the distance that the interviewers travel in order to cover their allocated assignment. So what we have done here is to define the fitness of our solution by looking at certain criteria. The first one is actually dispersion, then cumulative distance, further distance ratio, and check workload. Okay, I'll go through it one by one. The first thing is workload, which is defined as the number of respondents assigned to an interviewer. Okay, that is quite straightforward. Dispersion is actually basically the standard deviation of the workload across the assigned solution over the mean of the workload. Okay, this gives us an indication whether is there any big discrepancy between the interviewer with the most number of assignment versus the interviewer with the least number of assignment. We want to make sure that there's not a big gap so that the equitable workload criteria is sort of maintained. Okay? Then for the cumulative distance, we basically define it as the sum of the distances from the location of an interviewer, where he stays, to the clusters that were assigned to him. Because we don't want him to travel around the island to actually interview the respondents. And then the furthest is actually a metric to measure the distance between a pair of clusters. Again, for a particular interviewer, he's assigned, let's say, X number of clusters. We don't want the clusters to be spread across the island. We want the clusters to be concentrated relative to where he's staying. So this furthest distance measure will sort of give us a feel how spread out are the clusters that were assigned to him. Okay? And then the distance ratio is basically the cumulative distance divided by the distance to the nearest cluster. Again, this gives us a sense of how far he has to travel to cover the assignments given to him. And the check workload is basically to ensure that no interviewers will end up with no assignment. And also, no cluster will end up with no interviewers assigned to it. Okay? And basically, the different criteria are actually weighted by W1, W2, W3, W4. These are all design parameters that the students actually, through empirical simulation, then decide the best settings. Okay. Now, in order to show the performance of our modified PSO algorithm, I've used a test problem where here there are about 250 red dots or respondents, and we have 8 interviewers. So the problem is actually to assign these 250 respondents to these 8 interviewers. I can't use the full set because otherwise you won't be able to see anything. Right? Okay. So what we have done is to use this toy problem to illustrate the performance of our modified PSO algorithm. Okay. So this is the empirical setting that the student has derived through simulations. And by running the modified PSO algorithm on this small test problem, you can see that for interviewers 92, 94, 100, 101, 104, 105, it actually sits within the mean of 30 because we have 250 respondents and we have 8 interviewers. So on average, each interviewer should have about 30 respondents assigned. So you can see these are within the sort of design criteria. The only sort of problem you see here is where interviewer 119 has 46 respondents and interviewer 166 only has 8 respondents. So what happens here? Okay, we'll later look at the situation and try and find out what's the reason. Then the distance covered by the interviewers in order to actually serve all these respondents, you can see that actually the distribution of distance is not too bad. Okay, we have a standard deviation of about 5 kilometers. And this is the performance of the modified PSO algorithm on the test problem across the number of iterations, you can see that the solution more or less actually converge quite nicely at around 45, iteration number 45. Okay. So this is the solution visualized and color-coded based on the output of our modified PSO algorithm. You can see that the problem that we see just now, 119 and 166, they are actually very close. These two respondents are actually staying very close to one another. So there's some sort of racing condition to actually be allocated to respondents that is near them. That is why 166 received only 8, whereas 119 actually received 48 respondents, which will require some manual adjustment in this case. Instead of relying on the algorithm to actually fully give us a functional solution, we have actually manually adjust the solution here. But for the rest of the interviewers, you can see that the algorithm appears to be working as it has been designed to do so. For example, for interviewer 94, which is staying in the western part of Singapore, it receives only, this person receives only respondents that are staying in the western part, okay, and not on the eastern part. You don't see any respondents on the eastern part of Singapore assigned to this respondent. Similarly, the respondents staying near Changi are assigned respondents that is staying also on the western, on the eastern part of the island. And you have people staying in Bishan, Toa Payoh area, carrying respondents from the same region and also to the northern part of the island. Okay, so basically the discrete modified PSO algorithm that we propose seems to be working as what we expect it to be. Okay, so in order to do further analysis, we basically compare this new discrete particle swarm optimization technique with a heuristic technique that is basically a manual process done by one of our colleagues to manually assign these 250 respondents to the 8 interviewers, and also a random assignment strategy where we basically randomly assign the clusters of respondents to the 8 interviewers over 20 different random trials. Okay. So this is the allocation map for the heuristic approach. You can see that it's very different compared to the solution proposed or derived using our proposed discrete technique. Okay. Here, our colleague basically manually assign the respondents using, I would say, something like a greedy approach. So you can see that for respondents that is staying, like interviewer 166 that is staying in the southern part, this interviewer is still assigned respondents that is staying in the western part of the island, and so on and so forth. So you can see that the solution is not so clustered, and the assignment seems to be biased towards minimizing the distance traveled, and also trying to strike a balance between the workload of the interviewers. Okay. We then plot the solution from our discrete PSO versus the heuristic versus the random assignment strategy, and we basically look at 2 criteria, the total workload assigned and also the total distance traveled. So you can see that for the discrete particle swarm optimization technique that we propose, it's not so good at optimizing the total workload, ensuring an equitable workload across the different interviewers, but it's actually able to optimize the distance traveled by the interviewers as compared to the other 2 solutions. Okay. When you actually look at the standard deviation of the distance traveled and the standard deviation of the workload, our solutions still actually perform quite good with respect to heuristic and, of course, the random assignment. Okay. So in summary, we have actually proposed a discrete version of the PSO algorithm to actually deal with our interviewer respondents assignment problem in this particular project. And we have actually benchmarked our approach to the heuristic manual approach and also to the random assignment strategy. So going forward, in order to further improve the solution, we have to study how to control the initialization of the particles. Because currently, the solution is actually, start off with random initialization, meaning the particles are actually scattered all over the domain search space. If we know where the promising areas of the domain search space is, we can actually manually control the placement of the particles. And also, we can probably look at inspiration from GA, where they actually have some mutation to actually perturb the solutions. Currently, there's no any perturbation or mutation of the solutions to actually maybe strike a better balance between exploration and exploitation of the algorithm. Okay, so that's the end of the. Any questions? I'll be happy to take any questions that you may have.
So why you decide on PSO from the very beginning?
Because at the time, PSO is actually, I would say, we came across this PSO technique, and we are keen to see whether we can actually apply it to any of our live project. That's how the idea of this project came about. Basically, we scope it out such that the student is able to learn something about PSO. We are also able to create a win-win situation where the company probably is able to get a solution by exploring other techniques instead of the standard optimization technique that we are probably familiar with, like integer programming and stuff like that. Yeah.
So you did try integer programming?
Not really, because due to the lack of time, the student did not have time to do a lot of benchmark. Because a lot of the effort actually goes into geocoding the residential addresses to the lat long coordinates and to perform the clustering and so on. The solutioning of the work actually took quite a fair bit of time before the student is able to actually start working on the PSO algorithm. Yeah.
So Mr. Fa, how do you get NUS students to
Okay, because at that time the management was actually quite supportive of the data science team engaging with our academic partners because they believe in the value of a strong industrial academic relationship where they are trying to also attract bright students from NUS, NTU to go and to actually take up positions within the company when they graduate. And also because that time the data science team was set up with funding from I think, can't remember which agency, probably MOE. So part of the KPI was actually to engage the academic partners so that there's exchange of ideas between the industry and also academic. Yeah.
So it's not like students interning, like do some intern at the company?
We also do, at that time, we also do offer internships. So we actually have interns from NTU, NUS, and SMU. Yeah. In fact, I personally supervise a master's student from SMU, from the School of Information Studies. Yeah.
Actually, I was there in one of the, I think 2 years ago.
Yeah.
There was this Singapore statistics conference.
Oh, okay.
And actually, one of, I think, Newsom.
Yes. Yeah. Yeah. I think we presented similar work before. Yes.
Okay, yeah.
Okay, yeah.
And by the way, you mentioned it is published in somewhere, so can you say you will give us the reference?
Yes, I think the link was actually on one of the page. Yeah, here. So,
Oh, okay.
yeah. Yeah.
Sorry, I missed something. What's the fitness criteria you are using?
Okay, the fitness criteria is actually a combination of several different sub-criteria. This one is the fitness function that we use. Yes, yeah. Basically, we are still trying to actually strike a balance between workload equity and also the minimum distance travel by the interviewers.
And then the WIs are just sort of...
These are basically design parameters that the students have to actually empirically optimize.
Oh, but the W's are the weights, right?
Yes, the weights.
Which one seems to be more important?
Let me see, can't remember. Yeah, I think W3, which actually is the weight for the distance between the pair of clusters, the spread of the clusters
so those
assigned.
Are pre-selected, right?
Sorry?
Those are pre-selected constants.
Yes, pre-selected constants. Yes.
Can you go back to this? The whatever.
This one? Yes. Yeah. Yes.
Was the solution actually implemented?
The solution was actually partially implemented because this is not the entire solution. Here I have actually sort of simplified the problem for the student so that he can actually produce something workable within the given time frame. Here we only look at equitable workload and distance. We have not looked at constraints on, let's say, language. Especially for older folks, they may be able to only converse in their own dialect. The interviewers will also have to be matched to the language used. So this will further complicate the fitness function that we use here. Yeah.
So the final solution implemented is still based on PSO?
Yes. PSO as the first cut, and then as I say, the PSO algorithm is not able to give us the perfect solution. So we have to actually manually adjust the solution as well. So as seen here, the PSO maybe gave us up to 80% of the solution, but we still have to manually do some manual adjustment. Yeah.
But I think for those two you found, they were just, because the two,
Yeah, yeah. Yeah, so we still have to manually go through the solutions produced by the PSO algorithm and perform manual adjustment as and where is required. Yeah. But at least it's still better than having to manually assign 32,000 respondents to 100 interviewers. Yeah.
Have you tried this on other music projects?
No, unfortunately not. Yeah. Actually, I left like probably a year after the completion of this project. Yeah.
The cluster size, is that an issue?
Yes, cluster size is also a design issue. The more clusters you have, then you will have more granular assignment. Then the bigger clusters you have, then you have less flexibility in terms of trying to balance the workload.
So here, how many per cluster?
Here, for this small problem, I think we look at about 25 to 30 clusters.
So those are specified, right?
Yes, those are specified. Correct, yes, yeah. But you also don't want to have too small clusters because the rationale of the solution is actually the same clusters where respondents are actually staying more or less close together are actually assigned to the same cluster and then assigned to the same interviewer.
So this resembles or has, I think, very interesting applications to designing cluster randomized trials.
Correct. Yeah, I mean,
intervention studies in healthcare, right?
yes, yeah.
The clusters, everybody assumes is constant because you can work out the math a little bit, but in reality, the cluster sizes are different. You have no control over that.
Correct, yes.
So, given some power function, you want to allocate, decide how many clusters to use. And then the question is also the cluster sizes, they are unequal in practice.
Correct, yes, yeah.
So this might have some
Yeah.
interesting applications.
Yeah, definitely. I mean, in terms of theoretical research, you can, from this problem alone, you can think of a lot of different sub-problems to actually tackle.
How do you handle the constraints? You say there are constraints, right?
Yes. So constraints is one workload is actually one of the constraints. Distance travel is one of the constraints. Languages use is another constraint, and then also timing of the interviews. Because like I say, we have actually to schedule the timing of the interviews. So that is another constraint. So all these constraints become operational constraints. When you put everything together, the solution becomes very complicated. Yeah, so we can only simplify part by part and then try to optimize part by part.
Oh, okay.
Yeah.
So basically, you sort of look at, for each part. Okay.
Correct, yes, yeah.
And then you put them together.
Correct, yes.
And this particle, this PSO is supposed to enable you to do it, am I right?
This PSO only helps us to solve part of the, give us part of the solution, yes, yeah.
So at the end, you still have to look at the global.
Correct, yes. We have to apply different PSO and then probably through some manual combination of the solution together, yeah. Because we can't actually, we have tried to lump everything together, but then the fitness function becomes very complicated. Yes, yeah.
So how long it takes to
Running is actually pretty fast. Actually, about half an hour, you can actually have the solution for the complete 32,000 assignment. Yeah.
But I think actually one thing is because you are talking about Singapore.
Yes, correct. Yes.
But I think in the talk, 2 years ago, I remember it was about Indonesia.
Indonesia is another project.
Right.
That is not using,
really,
that is not using PSO.
That's
Yeah.
actually much more difficult.
Yeah. Yes. Yeah. Because in Singapore, at least you have a postal code, you have a unique leg long address.
And also, I think when you talk about distance travel, I think you can always take the subway, right?
Correct. In fact, the distance travel, we are using only very simple straight line distance. We are not even using the Havershine distance where you actually consider the curvature of the earth and things like that. Yeah. So, like I said, this is a very simplified problem statement for the student to actually work on. Yeah.
Because actually, I'm just curious, why the distance in Singapore, if you take the subway, is quite fast.
Correct. Yes.
It's
Yeah.
also cheap.
Yeah.
So.
Yes. The cost of travel we have not taken into account. Yeah. We only look at the absolute distance, straight line distance.
So are you applying PSO where you are now at APS?
No, we are actually dealing with more of a traditional upsell, cross-sell propensity scoring models in DBS. Yeah.
But I believe there are actually a lot of applications in investment portfolio management, minimizing risks.
I'm not with the risk group, but we have a few projects on recommender system. So we are now working on recommender systems.
Any more questions for the speaker? Well, if not, thank you again.
Right. Thank you.